Alright, so let me proceed to something called the cosmological constant of vacuum energy. Now the Einstein tensor, the reason we put Einstein tensor on the left hand side of this field equation, remember we proposed an equation of the form alpha G mu nu, and the reason we put G mu nu is that it's symmetric and divergence free and contains second order derivative of G. Okay, at most it has first order and zeroth order derivatives of G as well, but at most it contains two derivatives of G. Now it turns out the Einstein tensor is not the unique tensor with these qualities, and let's not forget that we also have G mu nu, the humble G mu nu, the metric itself. We know that if we are using Levi-Civita connection, the metric is also divergence free. And the metric is also a symmetric tensor. And metric has zero derivatives of G, so it's also allowed. So perhaps one should consider a general linear combination of big G mu nu and little G mu nu, okay, in the LHS of Einstein field equation. So this is what I have done with G mu nu plus some linear combination with little G mu nu, and this constant is called, which appears in this equation, is dimensionful, and it is called the cosmological constant. Now we can ask what is the dimension of this lambda? Well, the metric we will take to be dimensionless, G mu nu, because remember G mu nu is defined from the line element, which is dx nu times G mu nu. This has length square dimension. The coordinates also have length square dimension, so that means G we can take to be dimensionless. So G is dimensionless. About big G is made up of R, Riemann tensor, and the Riemann tensor or the Ricci tensor, which is defined in terms of the Riemann tensor, which contains terms like gamma, del gamma. And gamma, you should know, is made up of terms like G inverse times derivative of G, some terms like that, right? So clearly, G inverse and G, if G had dimension, they would cancel each other because G inverse and G have inverse dimension. So gamma has dimensions of this derivative, which is 1 over length. So this is 1 over length, and R, which is another derivative of gamma, has 1 over length squared. So this would be 1 over length squared. So gamma has dimensions. This similarity sign means it has dimensions of 1 over length. And the Riemann or the Ricci has dimensions of 1 over length square. So this has the dimensions 1 over length square. The Einstein tensor has dimension 1 over length square. Now this has dimension 0. So lambda must have also have dimension 1 over length square. Okay. So dimension of lambda is same as the dimension of 1 over length square. Okay, so it's a dimension-full constant. Okay. So when we add this term proportional to G mu nu in the Einstein field equation, then we call it the Einstein field equation with the cosmological constant term, Einstein field equation with the cosmological constant or cosmological constant term. And this cosmological constant was first introduced by Einstein himself. Now let me write this Einstein field equation with the cosmological constant in a slightly different way, which cosmologists do. So one can shift this to the right hand side and pretend that this is like some kind of energy momentum density, energy momentum stress tensor for just empty space. So T mu nu comes from matter, and then we can pretend that this contribution is the source of gravity in empty space, okay? Because this is proportional to the metric itself, so it's a property of the space. So think of it as a source of gravity in empty space by bringing it to the right hand side, and then we call that vacuum energy because it is certainly not the energy stress tensor. So I've written it this way: G mu nu equals 8 pi G Newton to the fourth times G mu nu plus Timonov vac. This Timonov vac means vacuum energy, which is given by this. And you can check that if I plug this here, I'm going to get back this equation. So one can move this cosmological term to the right hand side and pretend that it is a source for gravity, which is called vacuum energy. That source is called vacuum energy. Now, this is a bit peculiar because let's consider the two cases when lambda is positive and negative. If lambda is positive, then you can, if you remember, 1 component will give you the pressure P, and because of this minus sign, so this is positive, all these constants are positive, and eta G11 is also a positive number. So minus lambda times G11, something like that. So it is going to be a negative pressure. Okay. So if you think of the cosmological constant as stress tensor, the source of energy, the source of gravity, then you have to deal with the fact that it has negative pressure, which is not a very physical thing to have. In fact, as most of you know, negative pressure means second law of thermodynamics is violated. So it's pretty much pretty unlike matter. It's not a good way to think about the cosmological constant as a source of gravity. And if you consider the other case, which is when the cosmological constant is negative, and you might think that, well, let's take a negative cosmological constant. That might be good because pressure becomes positive. But then you can show that the 0,0 component of P becomes negative. Okay, you can show that it has negative energy, which is also bad. Okay, so either way, positive and negative, you have to deal with the cosmological. If you think of the cosmological constant as some kind of energy momentum tensor corresponding to some source that has unphysical properties, so it's better thought of as on the left hand side. This is what I will do. All right, so the last item today is the Einstein-Hilbert action. And the idea is that the field equations, which we wrote down, can be obtained by extremizing an action, that is, from a variational principle. So this action must be invariant in the general coordinate transformations. This is the property of the action, that if your system has symmetry, the action must be invariant, scalar under those symmetries. And for gravity, we know the gravity is invariant under general coordinate transformations, so the action should also be invariant in the general coordinate transformations. And varying the action must lead to the equation of motion. That is, it must contain the equation of motion with the second order in the metric derivative. Okay. So these two requirements are enough to determine what the action is. And this action is called the Einstein-Hilbert action. It consists of two parts. I'm writing the action I for action. Some books will have S also. Both are fine, but I'm using I for the to denote the action. Typically they use S in the literature, but you can also find I. So I sub EH is the Einstein-Hilbert action, and it consists of two parts. One is the gravitational part, gravity part, and the other is not gravity. This G is for the metric, so it's a contribution to the metric, and M is for matter. Okay, so the part which contributes from the metric is this. There's some dimensional factors which are there for dimensional reasons, and as you can see, we have quantities which are invariant on the general coordinate transformations. So this, as I mentioned, is the general coordinate invariant volume element, and R and lambda are individually scalars. So as you can see, the whole action, the IG, at least IG part of the action, is manifestly a scalar, obvious. The matter part is written this way. It is a space-time integral of this volume element times some matter Lagrangian. L sub M is the matter Lagrangian, which will depend on the particular kind of matter. You can take scalar fields, you can take point particles, you can take fermions, you can take Maxwell field. So it will depend. L sub M will depend on the particular matter fields. But this part, the volume measure, will be universal, it will be the same, and then you have to integrate over all space and all time. So the only condition on this matter Lagrangian is that the matter Lagrangian must be a scalar under general coordinate space. Okay, it must be a pure scalar under general coordinate space. So the idea is that now that we know both terms, we have to see how the action changes under variation of the metric. If I change the metric, how does the IEH vary, which is to say how does individually IG and IM vary, and then we have to demand that the variation is 0. That will give you the equation of motion. So let's do that. I'll be very schematic about this. The details can be found in the notes, and you should also try to work yourself. Now, let's first concentrate at the IG part. Let me try to take variation of this. And the variation of this will consist of this variation and plus a term in which root g is there, is paired, but we have to take variation of this second term. Okay, so there'll be two terms. So the first term involves varying the square root of minus g, the metric determinant, and you can show these steps. Please refer to the note for the details. I've skipped the details here. It's not very illuminating to do the algebra during the lecture, but the idea is that you have to know. In general relativity, it is very important that you know how to vary or take derivatives of the determinant of the metric. The determinant of the metric will appear everywhere, and it's an important result to know, or important derivation to learn, is to how to take the derivative or variation of square root of minus g. And if you do that, follow the steps in the notes, then you'll see it is given by this result. So the metric inverse is involved, and I've written the result in terms of variation or derivative of the metric. So the measure, from the measure you get this contribution. Now we also look at varying of R. So remember, R is made up of the Ricci contraction of the Ricci tensor. So when we vary R, we have to vary the metric, and we have to vary the Ricci scalar. Varying the metric is quite easy. You can show, again, refer to the notes, that is related to the varying of the variation of the inverse metric is related to the variation of the metric with some minus, with a minus sign and a couple of factors of the inverse. This is pretty much trying to take variation of 1 over x. Then we know the result is minus 1 over x squared times delta x. So we have g is inverse of the metric, so 1 over x, we have two factors of the inverse, and then delta of x, where x is g. You can think of the x as g. And then finally, we have to take the derivative of the variation, not the derivative, sorry, the variation of the Ricci tensor under variation of the metric. And for that, we will go to the definition of Ricci tensor in terms of the contraction of the Riemann tensor. And then we can show that the variation is equal to given by the covariant derivative of the variation of the Levi-Civita connection. The covariant derivative of the variation of Levi-Civita connection. Okay. So as you can see, the delta is inside, and then we have taken a covariant derivative. So this requires some algebra or some steps which I have not shown here. Please refer to the notes. If you do that, do all that, so you can show that if I gather together variation, delta of IG, the metric part of the action. If you do that, then you can assemble the terms which contain del G mu, which would be this term and this term. Okay. If you do that, if you gather those terms, including the cosmological, you'll get something which is, apart from the volume measure, within the square brackets, you'll have a term which is proportional to the variation of the metric times this quantity, G mu plus lambda G mu, and the total divergence term which comes from the because these are total divergences. So I've separated them out. The reason is that they will not contribute to the equation of motion because total divergent quantities can be dropped. So that's why, of course, in the presence of boundaries, this term might not. Total divergence, when I integrate over all space-time, it will contribute to a boundary piece at infinity. And for this integral to be well defined, those boundary pieces will vanish. So if it's full space, if this integral is over all space-time, then of course this total divergence gives zero contribution and it drops out. However, if my space-time has some boundaries, then this total derivative will give to a surface term, which you have to think about canceling some other way. And that can be done. I'm not discussing that complication, but that can be easily done using something called the Gibbons-Hartung York correction, which I will not discuss. But let's assume we are doing our manifold doesn't have a boundary. It is like Minkowski space. It extends all the way to infinity, and is non-compact. And for non-compact spaces, this total divergence would integrate out to zero. Then we can drop it. So the variation of the first term is done. Now we should look at the variation of the second term in the action, which is the matter. Now I'll be very, as I said, since we don't know the details of the matter Lagrangian, we can only do it formally. So as you can see, this. So people who don't know the rules of functional differentiation will not be able to follow why I wrote this. But this is basically a generalization of the chain rule which you learned in multivariable calculus to functional calculus. And the idea is that if I vary this derivative times LC, and I have to integrate over all x, because one can think of g mu as a variable defined at each position in x, each position in space time, sorry, each location in space and time. Okay, so then this is actually a generalization of the chain rule formula we use in multivariable calculus. Okay, so and then this functional derivative, this curly delta divided by curly delta, this is actually something that is called a functional derivative. And this is not the course where you learn this. Typically you learn functional differentiation in a course in field theory, so I will skip it. It is not going to be important for us in the remainder of the course. But just for the sake of today's lecture, where we do this variation, I will introduce this quantity. So this derivative is proportional to T mu, the stress energy tensor of the matter, and up to this factor of twice over square root of minus g. So this square root of minus g was necessary because I want to convert this volume element into the general coordinate invariant volume element. That's why I divide by square root of minus g. And then this half factor is conventional. Actually, it's not conventional because if you keep this factor of 2, you indeed get the correct energy momentum density you expect from a point particle or fluid if 2 is necessary. And if you do that, so now we have taken variation of both the metric part and the matter part, and we can combine these together into variation of the full action. So this is it. You have g mu plus lambda g mu, little g mu, minus, you get a contribution from the, so I got this minus sign because I took out overall minus sign here, okay? So I got a minus sign. And the rest of it will come from the matter, which is 8 by g mu plus g mu, plus a total divergence, which I can forget about it because we're considering a non-compact space. So demanding this action now vanishes for arbitrary variation of g mu would imply this has to vanish, which is the same as the Einstein field equation with cosmological constant. So this Lagrangian works. So we saw this action works, and it's an important part of the education of students learning VR to know the Einstein-Hilbert action. And let's provide a summary and outlook for what we did today. We introduced the Ricci tensor and Ricci scalars as contraction of phrases of the Riemann tensor. And in the process, we also got acquainted with the Weil tensor, which measures tidal distortion of shape but not of volume. We then constructed the Einstein tensor from the Bianchi identity for the Ricci tensor. And once we had the Einstein tensor, we could write down the Einstein field equation with and without the cosmological constant, which are the field equations are the equation of motion for the gravitational field. And as I said, it's a very key milestone for our course. And finally, we wrote down this Einstein-Hilbert action, which gives you the variational principle approach to general relativity. You start from an action, you vary the action, and you get the field equation. Okay. So up next is linearized Einstein field equation, which will turn out to be same as pure Pauli. I will motivate that the field equations are extremely difficult to solve, so perhaps a simpler job is to linearize it and then look for solutions. This is what is the agenda for next lecture. And then we will see that in linearized Einstein field equations, the solutions are those of waves, wave-like or gravitational waves. And then we will do a study of gravitational radiation. All right, we will end here. Thanks very much for your attention. And I'll see you in the next lecture.